All right, well, I want to thank the organizers for a great workshop and for inviting me. It's been a real pleasure. I don't ordinarily show off all my talents at once, but I'm going to do a little mind-reading trick and predict that every one of you is thinking the same thing, which is, how late am I going to go into lunch? So my job is to get you to stop thinking that and to think that Central Southwest Asia, which is a part of the world that you may not have thought that much about before, is actually very interesting from a drought point of view, and I would argue is a region of the world that the community maybe should focus a bit more on. All right, so let me orient you. Here's a map of severe drought for a particular, I think, 4-year period, 3 or 4-year period, 1998 through 2001. It's a measure of extreme drought, doesn't really matter too much which measure you use. Darker browns are the severer drought, and you can see that there's this huge bullseye of drought right in this part of the world. And that's what initially drew our attention to that region. And for the purposes of this talk, that red box is what I'm going to call Central Southwest Asia. There are a couple of different geographical names, but that's probably about as good as any. So this was an exceptionally severe drought on the global scale, which I'll say a little bit more about in a minute, but I just wanted to orient you a little bit on the region and the climate of the region. So on the left is the topography. At the Tibetan Plateau, the Himalayas, you have the Hindu Kush, a lot of high mountains in this region. And in the upper left is the topography. In the upper right here is the cold season precipitation, November through April. And most of the region gets its precip primarily as snow in the winter. So here's the cold season, here's the warm season. So in the warm season, the only significant precipitation is the little bit of the monsoon that makes its way along the side of the Himalayas there, and it comes a little bit into Pakistan and Tibet into Afghanistan. So you do get a little bit of summer precipitation from that, but mainly it's winter precipitation for most of the region. This is NDVI, just to show you that there's a lot of desert in the region, but it's certainly not pure desert. It's arid to semi-arid, but there's a fair amount of population there. And the high mountains of the region are relatively vegetated. Actually, the lowlands, like in the lowlands of Afghanistan, western Pakistan, and Iran, there is some real like bare rock desert there, but it's not certainly completely desert. All right, I won't dwell too much on this, but the region has a fairly complex hydrology, 2 major river systems, the Amu Darya and the Sir Darya, and the Aral Sea. So here's the Aral Sea right here in gray, and this is the Sir Darya up here and the Amu Darya up here. So they drain from those high mountain regions, which actually collect a tremendous amount of snow, which then melts. And prior to the 1940s and 1950s, flowed into the Aral Sea and made it one of the largest freshwater seas in the world. So this gray area here is what it used to be. This little inset area here with all those little lobes is a more current. The Aral Sea has largely dried up, and here's a little map here of how it's shrunk over time from the late 50s through 2000. That has nothing to do with climate and everything to do with growing cotton in the desert, which was instituted under the former Soviet Union but has continued into the present time. So that's the sort of background water demand, but overlaid on that is a tremendous amount of climate variability, including severe drought, as well as probably a fair contribution from climate change as well. So this is an area that gets both natural severe drought, probably climate change, and has water shortages that are societally driven as well. And depending on who you ask, the Soviet Union, some people would say that the Soviet Union actually drew the boundaries so that the rivers cross as many countries as possible. But whatever the initial setup, the net result is that these major rivers cross, the rivers and watersheds cross all the countries in the local region. So the political issues here are tremendously high, and the US State Department actually thinks that water issues in this region are a high risk for conflict. All right, a few words about the drought from about 1999 through 2001 in this part of the world was fairly apocalyptic. And I, again, won't spend too much time here, but we have a couple of reports on this. Depending on how you count it, it affected more than 60 million people, economic losses in the billions of dollars, in terms of agricultural, major crop failures for multiple years throughout most of the region, in both non-irrigated and irrigated crops. The irrigated crops, the irrigation comes mainly from the water flow, the yearly water flow. So if you have a drought, you don't have a lot of big reservoirs in this region to irrigate and sort of get around that, especially after the second and third year of drought. Tremendous amount of livestock death in this period. I have some examples here. Here's an example in Iran. By the middle of the drought, water resources were cut in half. In terms of environment, some major wetlands, internationally recognized wetlands, completely dried up. And another example, economically speaking, during the first 2 years of the drought in Afghanistan, household debt doubled. Assets decreased by half. There's actually a lot of gender inequality in how the debt was distributed and how it affected people. And you don't perhaps often think of serious health impacts with drought, but because there's so little fresh water in the first place here, when you have a drought, not only does it affect your agriculture and your livestock, but you also have less fresh water for sanitation. There were huge millions of people migrating, refugees, drought refugees in this region during this period. So you had these huge health outbreaks: polio, cholera, diphtheria, typhoid, tuberculosis, particularly heavy in the refugee camps. So this was really, really, really extreme. And across many more dimensions than you might think of in terms of drought. All right, so the drought was bad. I think it's fair to say. There is a lot of predictability in this region, and I'm going to talk a little bit about the different flavors of predictability and why there's predictability in this region. So I would love to have a detailed discussion of the dynamics, but I should probably put that off. Suffice it to say, on some level, that the regional drought, the severe drought, and other droughts in the regions are linked to what's going on in the tropical climate, tropical ocean, things like El Nino. In this case, not exactly El Nino, maybe a particular flavor of El Nino, but there is very robust links between the drought variability in this region and the tropical ocean. So from that, you get a measure of seasonal predictability. Which is something that we've explored in several papers. The dynamics of the link to the tropics is not simple. There are some relatively simple aspects of it, but it actually involves a whole hemispheric circulation, which I won't get into here. That the influence from the tropics, the tropical ocean in concert with the tropical atmosphere, changes the winds over the region. The winds over the region change the precipitation, both through changing the moisture inputs into the region and through affecting the vertical velocity in a couple of important ways. But the main highlight I want to make here is that you can use that information, the state of the tropical ocean, which is varying slowly on seasonal timescales, to make predictability, to make predictions, seasonal predictions of precipitation for the region. And we've done that. Particularly Mike Tippett at IRI has taken the lead on that. And I'm not going to take you figure by figure here. This is just a little representative. So we actually have done cross-validated skills. We've done retrospective analysis of forecasts in this region. And the seasonal forecast skill is there. It's not great, although I think it's fair to say that seasonal forecast skill is not great anywhere. But there is some information, statistically cross-validated, significant seasonal forecast information for this region. And this is a little close-up of where the skill really is. So this is at Afghanistan here, and Pakistan, and Tajikistan, Turkmenistan, the Uzbekistan sisters up here. So the area where you have skill is somewhat limited, but it is there. There is some information. There's a lot more information direct just from first physical principles because the precipitation is primarily occurring as snow in the high mountains in the region. And there isn't much precipitation in the warm season. So the water you get in the warm season is primarily snowmelt. Water not only in terms of river flows, but also in terms of soil moisture for vegetation. So this is, in that sense, actually a very predictable part of the world because the hydrology, which drives the vegetation as well, is directly predictable if you know the snowpack. So here's a little box average. Here's a little box showing these red dots are river flow data. So river flow data is very patchy in this part of the world. There are actually good river flow data during the Soviet Union period for the former Soviet Union states, so excluding Afghanistan. But we do have a nice cluster here in the high mountains of the region, so we can look at that fairly carefully. So here's the water year, October through September. This is the seasonal cycle of precipitation for this box region, and black is precipitation. So you can see that it peaks in March and April, and then there's this lag. Here are the river flows in this bluish color. That's a good 2-month lag between the peak river flows and the peak precipitation. And the NDVI, the vegetation, satellite vegetation index, peaks another 2 months after that. So if you know how much precipitation, most of it's falling as snow. So if you know how much precipitation there is, you know about how much snow there is, you can then have very good understanding of what the river flow and probably a fair amount of information about the vegetation as well. All right, so that would be great if you knew the presentation. If you knew the precipitation. And of course, this is not lost on the folks of the region by any means. If you live there, you know that the snow on the mountains tells you what kind of a season you're going to have. The problem is knowing how much snowpack you have. We have difficulties with that in the US with a very good, well, a very extensive reporting system anyway. So knowing the snowpack, that information is hard to get at the high resolution you would need to be able to know exactly where it was going to go and how much of it there was. However, I will file this under one of Chris's happy thoughts. I think I might reorganize my life under Chris's, where's Chris? Under his happy thought organization scheme. So it turns out that because of the synoptics, the synoptic meteorology of the system, the amount of snowpack you have is actually readily captured by the large-scale flow and the large-scale precipitation. Okay, so these are high mountain regions. The precipitation in the winter is primarily coming from large synoptic storms that are tracking in from the west that primarily just completely rain out. So if you capture those synoptic systems fairly well, you actually get the net amount of snow actually quite accurately, or at least reasonably accurately. And those synoptic storms, while they're not well resolved over the region, they're very nicely resolved upstream over Europe because you have all those radiosondes, you have all that mechanism of monitoring going on, so you sample these storms very nicely upstream. And then they go over the region and basically precipitate out on the mountains. So what we found is, using the operationally available large-scale climate information, so like 2.5 degrees by 2.5 degrees, the stuff that's available in real time, you can actually capture the river flow fairly accurately. So what we've done is using a pattern-based analysis, although it's not sensitive to that. So what we've done is look at a CCA, canonical correlation, between the upper level winds, that's U, the zonal wind, the upper level winds and the precipitation in November through March from the large scale operationally available data. We can link those patterns of precipitation and upper level wind to April through August river flows, so the subsequent river flows. So you can do this in real time and actually get pretty high correlations, cross-validated correlations better than 0.5 for many of the river flow stations in the region. And you get the little rivers as well, not just the big downstream Amudarya and Sirdarya. So one aspect of this is very unsurprising. If you know the snowpack, and you know there isn't much warm season precipitation, then of course you can predict the river flows. What's nice about this is that you capture that relationship with the available operational large-scale data. So this is a very nice approach to that. And this is data that folks on the ground, they don't really think about it this way. They're thinking about more trying to monitor the local snowpack. So this is large-scale data that isn't, I don't think, really used in the region quite like this. All right, so here are some forecasts. The forecasts are in black. Sorry, the observed, these are anomalies for the Siridaria and the Amudarya. The observed anomalies are in open circles. The forecast is in black. These are hindcasts, so we didn't make these in real time. I haven't been making forecasts since 1986. But this data was withheld from the whole analysis, so it's a fair comparison. What we're trying to predict here was not used in the training data at all. And you can see that you do a pretty good job of predicting these rivers in the region. And you would expect this skill in real time too. So this is nice. Again, it's not surprising. If you know the snowpack, you know what these rivers are going to do. What's nice is that you can actually figure out the snowpack. All right. You can take the same approach with vegetation, which is what we're working on currently. This is a correlation map of the May through August, so the growing season vegetation correlated to the previous winter's precipitation. And you can see there's a lot of red here in some areas, and this red is greater than 0.8 correlation. This is not cross-validated. So the real forecast skill would be lower than this, but certainly the correlations are very high. And again, what this is telling you is that the vegetation in the region really depends on that snowmelt. There isn't much precipitation going on. There isn't much rain May through August. So what's causing the vegetation to grow is the snowmelt. And the irrigation is also related to the snowmelt because there aren't a lot of big reservoirs. All right, so we have been, this year we tried out an experimental NDVI vegetation forecast for this year. Apologize for the quality of the graphics. So we made a forecast. So this is NDVI May through August of this year. So this is a real-time forecast. And this forecast is based on the upper level winds, the jet level winds, and the observed precipitation anomalies for this past winter. And you see a lot of brown here, particularly up in the Tajikistan, Uzbekistan, Turkmenistan, well, I guess southern Kazakhstan, with a little bit of decreased vegetation in Afghanistan. Afghanistan actually ended up near neutral this winter. A lot of the rest of the region was in reasonably severe drought, which is why you see no greens there. So our forecast is near normal, slightly decreased vegetation for much of Afghanistan, but in some of these fairly fertile valley regions, we do expect to see decreased vegetation this year. Now we're still working on validating this and carefully delineating where we have skill and where we don't, but we think that this will has a fair amount of use. Now, in my last 5 minutes, or so you hope, I also want to point out that's all seasonal predictability. And again, you get seasonal predictability both from the links to the tropics and because of snowmelt. So you have two seasonal mechanisms for seasonal predictability. There is also intra-seasonal, so like 30-day time scales, 10 to 30-day time scales. There's also predictability in this region at those time scales based on something called the Madden-Julian oscillation, or MJO, which some of you may be familiar with, which is also tropically based. So the MJO is associated with heavy convection in this region of the tropics and actually influences Central Southwest Asia as well. This is one of the, well, it's really almost the only intra-seasonal aspect of the climate that we can predict well is the MJO. And it actually turns out to be fairly predictable because it's coherent and it moves relatively slowly. So here is a little schematic. This is actually Riyadh, so this is Saudi Arabia as an example. There are 8 phases of the MJO, so phases 1 through 8. And this green line is the average precipitation, cold season precipitation in Riyadh by phase of the MJO. So you can see that when it's enhancing precipitation in Riyadh, it's, I don't know, however many fold, 10-fold larger than when it's suppressing precipitation. In a lot of the stations in the region, the MJO has a very large effect. And you can see it related to individual floods in the region as well. And that's useful information because often in the midst of these fairly apocalyptic droughts that this region gets, you get some flooding, right? Just to add insult to injury. Once the ground is nice and dry, then a big flood can come in and just wash everything away. All right, and so here I'm showing these are precipitation anomalies over a big chunk of the globe. So here's the US, here's China, here's Southwest Asia, here's the Pacific. So this is November through April 2007 to 2008. So the cold season, 07-08, green is wetter than average, brown is drier than average. Big La Nina during this period, strong tropical forcing. The seasonal average was quite dry in this region. It was a big drought in this year. But if you look just at January, within that you actually see wet anomalies, and the tropical forcing in the Indian Ocean has switched sign. So for the season, it was a very strong drought. Iran bought US wheat for the first time in 30 years. Afghan wheat was down by 60%. There were power shortages in Iran because they didn't have enough water to drive the hydroelectric. So the season was this huge drought. But the month of January had heavy snow and avalanches in Afghanistan, hundreds of fatalities, massive livestock losses, heaviest snowfall in Iran for more than a decade. All right, so I don't know how many of you have family who are farmers, but it's hard not to really feel for a country that is having this devastating drought, and then for 1 month in the middle of that, they get epic snowfall, right? I mean, it's just, if ever there were insult to injury, this is it. And this actually was a fairly well predicted strong negative MJO. So this could potentially have been anticipated, at least in part. All right, and I'm just going to wrap up. So I guess there are 3 things I would ask you to consider about this region of the world. One is it has very severe droughts. 2, it has actually a fair amount of predictability at different time scales. I think what is lacking here, so there's a lot of opportunity, but it's obviously an area of the world with a lot of difficulties, and I don't think this information is really used very much in this region. We've had contact with different groups, but maintaining contact for more than a year is very difficult in this part of the world. So there's a lot of opportunity here, but the information is not being used a lot. So again, there are 2 sources of predictability here. One is climate variability, both the seasonal and the intraseasonal, El Nino and the MJO. That's one. The other is the importance of the snowpack. Chris's happy thought for the day is that large-scale climate data actually captures most of this information. The available data we have is good enough. And then the last point is that just fortuitously, by virtue of the climate of the region, you actually get a fair amount of information, not only at the seasonal timescales, but also at intraseasonal. So this is a region where you could provide meaningful updates on probably a weekly time scale as to whether there was going to be any heavy precipitation events in the midst of whatever the seasonal anomaly was. And I'll end there. Thanks very much.
Questions for Matthew? Yes, Dave.
An excellent presentation. I love it. 2
what will be the uncertainty with reanalysis, and how does that play into this kind of assessment?
Yeah, so the reanalysis is okay at the NSEP-NCAR reanalysis. The original NSEP-NCAR reanalysis is okay at the regional scale. So it doesn't get the local details right, but it knows the net amount of precip going in. The old ERA 40 is better. And in fact, there's another group that has shown that you can take the ERA 40 precipitation and run it through a basin model and make streamflow predictions that way. I don't know yet with the MERA or the CFS, but my guess is actually that they're better because, again, the synoptic scale is nicely sampled upstream, so it's really the interaction of that well-sampled synoptic with the local orography you get right. And that's something that as long as you have the resolution, you should be able to do a reasonable job at. So, so the old stuff is okay. The new stuff, I'm hopeful, will be even better, but I don't know yet.
Something similar we see for the Indian monsoon, for instance, and now we are seeing that there's a reversal that we can identify, that depending on the vegetation pattern, we can predict whether the monsoon is going to have a reverse feedback. Do you see that reverse correlation of your vegetation actually affecting the amount of moisture available for the precipitation to be affected?
The data that we've looked at so far is not good enough to address that, but my strong guess would be that yes, given how arid the region is, and the precipitation can change, or sorry, the vegetation can change pretty dramatically in terms of health, and the moisture sources are all reasonably remote. So my guess would be that there might be a considerable signal there, but we haven't had the resolution of data to look at that yet, the MET data.
Any other questions? Yes.
One quick question. The predictability that you are talking about, is that with regard to timeliness or the precipitation amounts too?
So the predictability we have comes in two flavors. The seasonal prediction is just predicting a net seasonal amount. The MJO, the only thing that we've actually formally shown, I think, is weekly averages of precipitation. So we haven't, we could, but we haven't had a chance yet to look at like onset dates, onset of the, you could also look at, we've done some synoptic composites, but you could also look at synoptic timing as well. But we primarily have looked at weekly averages or seasonal averages, not so much the timing, although obviously that's a critical issue.
Any other questions before lunch? Yes.
Just one quick comment. You know, Matt, I think this is really exceptional work. And it's really rare that people look at a system like this in all these different ways. And, I hope we can really talk about how.
Can I have a hug?
There's your happy though, right?
So, anyway, but I think we did. Here's the slide. That was the but I think that you know, you and I should really work together, because even though intellectually you really put together all this work, it's not really getting out there.
Absolutely.
So
Yeah, that's definitely one of my major points, is that we have not managed to, we've tried basically on an informal basis and have not gotten anywhere near the way that you guys have done. Yeah.
That wasn't too bad a slide. Anything else before we go to lunch? Okay, one more last round of applause for our speakers for this morning.